Over half a century, the official justification for naval nuclear reactors rested on a single promise: unlimited range without refueling. Navies spoke endlessly about the ability to circle the globe for decades without ever needing a tanker, and the public accepted this as the ultimate strategic prize. That explanation is now a relic of a previous era. The true reason every major navy is now racing toward nuclear propulsion has almost nothing to do with refueling. The modern capital warship has become a floating power station whose entire combat relevance depends on generating and sustaining massive electrical output while under attack. A frontline destroyer carries fewer than 100 vertical launch cells. And in a saturation attack involving dozens of cheap anti-ship missiles arriving from multiple axes simultaneously, those cells are empty within minutes. Once the last interceptor leaves the rail, the ship is defenseless regardless of how advanced its radar may be. The only practical solution is directed energy. A Megawatt-class combat laser can fire an unlimited number of shots as long as the ship can supply electricity, with each intercept costing a few dollars in electrical power compared to the $4.3 million required for a single SM-6 missile. On a modern destroyer, propulsion and electrical power are completely separate systems. The Arleigh Burke Flight 3 uses 4 LM-2500 gas turbines mechanically geared to the propeller shafts for movement, while all electrical power comes from 3 independent AG9160 generator sets with a combined output of just 12 megawatts. The SPY-6 radar alone consumes a large fraction of that budget, leaving razor-thin margins for any directed energy weapon. When the generators hit their ceiling, the laser stops firing, but the ship keeps moving at 30 knots because the propulsion turbines are entirely unaffected. China's Type 055 has more headroom with 30 megawatts from 6 QD-50 turbine generators, but even that is stretched thin by its dual-band radar and cooling under combat load. A nuclear reactor eliminates this split entirely, providing both propulsion and tens of megawatts of surplus electrical power from a single source with no generator bottleneck. The most insatiable power demand of the 2030s warship is not a laser or a catapult, but its own electronic brain. Less than break greater than next-generation combatants must function as floating data centers, running sensor fusion algorithms across inputs from dozens of drones, satellites, and underwater sensors in real time. According to industry estimates, a single rack of military-grade AI processors can draw 50 kilowatts, and the liquid cooling required to prevent those servers from melting can draw another 30. A conventionally powered ship forced to carry this cognitive load at battle speed must choose between moving fast and thinking fast. A nuclear ship does both, silently and indefinitely. The electromagnetic catapults on the Type 003 Fujian require a 45-second charging cycle, but so do the EMALS on the nuclear-powered Gerald R. Ford. All electromagnetic launch systems must spit up their flywheels and capacitor banks between shots, drawing power from the ship during the recharge period and releasing it in a 2 to 3 second burst. The true limitation of conventional propulsion is not the charging delay. It is the brutal fuel consumption that occurs when the carrier tries to sustain high-tempo air operations while maintaining 30 knots of speed. Fujian can sustain a high launch tempo in the opening phase of operations, but without nuclear propulsion it must reduce intensity far sooner to conserve fuel. The Fujian, commissioned in November 2025, is the world's largest conventionally powered warship at over 80,000 tons, and represents a historic leap for the plan as its first carrier equipped with electromagnetic catapults. However, it carries only 3 catapults to the Ford class's 4, with 2 at the bow and 1 along the angled deck. The flight deck features a narrower angle than American carriers, which restricts the ability to conduct simultaneous launches and recoveries because of overlaps between the landing strip and bow catapults. Independent analysts estimate the Fujian's sortie generation capacity at roughly 60% of a Nimitz-class carrier. United States is advancing the BBGX Trump class, a nuclear-powered heavy surface combatant, officially confirmed in the Navy's 2026 30-year shipbuilding plan and designed to serve as a floating electromagnetic fortress armed with lasers, hypersonic missiles, and massive sensor arrays. The lead ship is slated for procurement in fiscal year 2028 at a projected cost of $17 billion. France cannot operate its future-paying carrier on conventional fuel, which is why the design relies on twin K-22 reactors to power American-supplied electromagnetic catapults and the next-generation FCAS air wing. China, having learned the limits of conventional propulsion on the Type 003 Fujian, is now constructing the Type 004 with a nuclear power plant explicitly designed to maintain high sortie rates without turning the carrier group into a floating fuel convoy. Conventional Carrier Strike Group is tethered to a vulnerable logistical signature that adversary intelligence agencies can easily exploit. The group must rendezvous with slow, predictable fleet oilers every few days to stay on station, and those massive tankers are highly visible to satellite radar. An adversary does not need to find the aircraft carrier. It only needs to track the oiler, and the fleet's position is revealed. A nuclear-powered strike group eliminates the need for underway refueling, erasing that entire intelligence trail and allowing the fleet to vanish into vast ocean spaces for months without betraying its position. Conventional warships powered by gas turbines expel exhaust gases at over 500 degrees Celsius through large metal funnels, creating a heat plume that modern infrared and hyperspectral imaging satellites can detect with relative ease. A nuclear reactor has no exhaust stack. Its residual heat is transferred directly into the ocean through underwater condensers, dramatically reducing the ship's surface thermal contrast. When combined with the elimination of the logistical signature, this thermal stealth gives the nuclear fleet a ghost-like quality that fundamentally complicates enemy targeting in an era where no platform can truly hide. The Arctic is melting, and by the mid-2030s, the northern sea route will become a commercially viable corridor, cutting the transit distance between East Asia and Europe by nearly 40%. Russia has already militarized the region with a fleet of nuclear-powered icebreakers and new coastal bases, creating a strategic reality that conventional navies cannot easily contest. Conventional surface combatants cannot operate independently in ice-heavy waters because their logistical support tankers cannot follow them safely. A nuclear carrier or heavy surface combatant faces no such restriction and can project power along the emerging polar trade routes without a single vulnerable oiler in its wake, turning what appears to be a simple propulsion choice into a long-term bet on which nations will control the planet's newest maritime highways. When Australia tore up a $90 billion submarine contract with France and pivoted to the AUKUS Pact, it was executing the most elegant legal maneuver in modern non-proliferation history. The loophole is not found in the Nuclear Non-Proliferation Treaty itself, which contains only 11 articles. It exists within the safeguards architecture overseen by the International Atomic Energy Agency, specifically in paragraph 14 of the Model Comprehensive Safeguards Agreement set out in document INFCIRC 153. Under this mechanism, a non-nuclear weapon state may withdraw nuclear material from routine international inspection, provided that the material is used exclusively for a non-proscribed military activity, and naval nuclear propulsion was explicitly foreseen by the drafters of the NPT as qualifying for this exemption. Australia, a non-nuclear weapons state, will now operate nuclear-powered submarines fueled by highly enriched uranium that does not count toward its standard safeguards obligations in the same way as material destined for weapons programs. Under the trilateral AUKUS Naval Nuclear Propulsion Agreement, the United Kingdom and the United States cannot transfer any nuclear material to Australia for use in conventionally armed, nuclear-powered submarines prior to Australia having an Article 14 arrangement in place with the IAEA. The precedent is now set, and Japan, South Korea, and Brazil are watching closely. The AUKUS model provides a perfectly legal pathway for any technically capable nation to acquire the full spectrum of naval nuclear technology, along with all the industrial enrichment infrastructure that necessarily comes with it. A country cannot simply purchase a naval reactor off the shelf. It must build an entire domestic pipeline of nuclear engineers, precision metallurgists, and non-destructive testing inspectors who require decades to train. France deliberately uses its naval programs to preserve its nuclear workforce between civilian energy projects, while Australia, under AUKUS, faces a 20-year timeline just to produce its first cohort of certified nuclear-grade welders. This is not a shipbuilding program. It is a generational industrial mobilization that permanently locks a nation into the highest tier of advanced manufacturing. And the countries that start building this expertise today will harvest the economic returns for the next half-century. Technicians who can weld a submarine hull to nuclear tolerances command salaries multiples higher than ordinary manufacturing workers, and their presence pulls up the entire advanced manufacturing sector of the economy. Thousands of high-wage jobs radiate outward through the supply chain, structurally elevating the country's gross domestic product per capita in ways that no short-term stimulus program can replicate. A nation that enters the nuclear naval club does not merely acquire a new weapons platform. It restructures its entire industrial economy around skills and quality standards that take 50 years to cultivate and are extremely difficult to replicate without starting a naval reactor program from scratch. The enrichment facilities required to produce fuel for naval reactors simultaneously generate vast quantities of depleted uranium, a metal nearly 70% denser than lead at 19.1 grams per cubic centimeter. This material is not waste. The military uses it immediately to manufacture kinetic energy penetrators capable of punching through the frontal armor of any modern main battle tank, while the aerospace industry uses it as counterweights in the tails of commercial airliners. A single decision to build a nuclear submarine fleet cascades into a domestic supply of advanced armor-piercing ammunition and aircraft components that would otherwise require import licenses and strict diplomatic clearance from supplier nations. Decades, critics argued that nuclear warships were simply too expensive, pointing to the multi-billion-dollar price tag of a Ford-class carrier and the $17 billion projected cost of the lead BBGX. That calculus has now inverted. A single saturation missile attack can exhaust hundreds of millions of dollars in defensive interceptors in minutes, while a nuclear-powered laser can fire unlimited shots for the cost of electrical power alone. When calculated across a 30-year hull life, the high upfront capital cost of a reactor becomes the economically rational option, not the expensive one. The nuclear fleet is no longer a luxury. It is the only affordable way to survive an era of massed, cheap threats. A single Ford-class carrier generates more than 100 megawatts of usable electrical power from its two A-1B reactors, which produce approximately 700 megawatts of thermal output in total. That is more than triple the electrical capacity of the previous Nimitz class, and enough to supply a small city. When a cyclone devastates an allied island nation and destroys its power infrastructure, a conventionally powered hospital ship can stay for only a few days before its fuel runs low. A nuclear carrier can anchor offshore and provide electricity, desalinated water, and airborne medical evacuation coordination for 6 months without interruption. It is the ultimate soft power instrument, projecting not only lethal force, but also the promise of permanent, self-sufficient presence in a humanitarian crisis. When a large, nuclear-powered surface combatant or carrier enters a contested maritime zone, the adversary faces an unresolvable intelligence problem. No external sensor can determine whether the nuclear reactor is solely for propulsion, or whether the vessel also carries tactical nuclear warheads among its weapons load. The ship does not need to make any explicit threat. Its mere presence, enabled by the properties of its power plant, forces enemy commanders to factor in a catastrophic worst-case scenario they cannot disprove, compressing their decision cycle and introducing a hesitation that conventional platforms simply cannot create. Going nuclear is not about building a better warship. It is about securing a permanent seat at the highest table of geopolitical leverage, where a navy becomes simultaneously a fighting force, an industrial accelerator, a legal instrument, an economic multiplier, and a psychological deterrent that adversaries cannot fully calculate. The countries chasing nuclear propulsion are not preparing for the last war. They are locking in the architecture of power for the rest of this century. And that architecture runs entirely on megawatts.